So our purpose for lecture 10 here is mostly review and to go in a little bit more detail about some of the control survey concepts that we've talked about earlier on with respect to leveling and angle measurements and traverses. I just want to make sure that you have a solid understanding of state plane grid-based coordinate systems and some of the basic concepts in the discussion of geodetic versus grid coordinate systems, distortion, and some specifics about Oregon's state plane coordinate system. So not a lot of calculations here, mostly conceptual understanding, but just like the last few lectures, you see that a lot of this is review of things that have come up in earlier chapters or earlier lectures, and we're just getting into it in a little bit more detail and a little bit more application. So we're going to talk a little bit about the basics of control surveys, or survey control, I guess is often called as well. We'll talk about geodetic reference systems versus grid coordinate systems. They both serve a purpose, but we primarily focus on grid systems and engineering work. And then we'll talk a little bit about if you were on a survey crew setting up the survey control for a project, what would be some best practices about that? How you tie into references, how you set other control points, intermediate control points, basic stuff like that. A lot of it's common sense, but good stuff for you to be thinking about moving forward. So, why do we have survey control? What is the whole purpose of setting up a reference network so that we can tie into it when we're doing surveying? Well, I think it should be at this point pretty self-explanatory to you that we need to be able to precisely locate and accurately locate whatever we're surveying relative to the world or relative to a local grid system. We need to know where things actually are. And that should seem like it's pretty easy to do, but there's so many different ways to define location and things like mean sea level. What does that even really mean? And elevations are all based off of that. And when it comes down to measuring, latitude and longitude, for example, those are relatively well defined. But when it comes to the shape of the Earth, latitude and longitude are basically, for the most part, assuming that it's perfectly spherical, but we know that in fact it's not. So there are distortions that happen as a result. So making sure that everybody is referencing the same point, regardless of which system they're using, takes a lot of effort. So those are the multiple challenges that I'm talking about down below. How things get referenced relative to other things should be straightforward. It's not, but it's a critical part of what we do. And you'll see in the next lecture and in chapter 14, this becomes a legal issue a lot of the times where we're defining people's property boundaries as surveyors, and that has legal ramifications associated with it. So this is all very, very important, knowing what you're measuring relative to, and being able to convert between different ones is a really important skill to have. So let's just refresh our memory a little bit. When it comes to geodetic reference, we're talking about references that take into account like the oblong spheroid or ellipsoid shape of the Earth. So this is how we define things like mean sea level. This is how we define like the center of the Earth. And these are some broad parameters associated with different reference systems. Some of them more historic, some of them more contemporary, but like flattening coefficients for this oblong spheroid, semi-major, semi-minor axes, the distances for each of them. But this is what when we say like mean sea level, like oftentimes that's what these are intended to define. But again, it is like the actual curved Earth. This isn't anything that then gets projected onto a two-dimensional surface. That's what grid coordinate systems and state plane coordinate systems are for. This is just about the actual study of the curved Earth itself. And when it comes down to like the accuracy and the precision with which we do that nowadays, it's pretty mind-boggling compared to where it was just 50 years ago. So the advent of um, GPS and these high accuracy reference network systems, HARN, it's pretty incredible. So some of these errors are 1 to the 100 million. Especially with a long enough amount of time and a sophisticated enough processing unit, you can get pretty incredible accuracies when it comes to setting the reference network for these geodetic coordinate systems. So again, because this kind of forms the basis for how we tie in a lot of our surveys, it has to be very, very precise. We've seen that before with a lot of the closure parameters, things like that. But either way, very small amount of error because of the high precision tools that we now have at our disposal. However, as I mentioned before, and this is just more of what we were just talking about a second ago, almost all of your work in engineering, whether it's on the surveying side or more likely on the design side, is going to be based off not geodetic coordinate systems, but grid coordinate systems. So grid coordinate systems are a useful approximation of the curved surface of the Earth. Whereas like the geodesy and the study of the curved shape of the Earth and is useful in terms of setting these grid coordinate systems. The grid coordinate systems are really what we use on a day-to-day basis. So the purpose for it is that we're used to drawing things onto two-dimensional sheets of paper, and nowadays, mostly digital PDFs, stuff like that. But either way, that isn't the curved surface of the Earth. And so the way that we approximate it kind of takes one of two main forms that we'll talk about in a second. But generally speaking, it involves taking the curved Earth, putting like something on top of it that we can then project points out to. What we're putting on top of it might still be like a three-dimensional shape, but a three-dimensional shape that can then be like unfolded into 2 dimensions. So the two shapes that we're going to talk about would be a cone and a cylinder. Both of those, if you cut a slit in it, would then become a two-dimensional flat representation. But that inherently causes some distortion, and so we need to be able to quantify what that distortion is in order to then minimize it. And there's multiple ways that we can minimize it. Usually it simply means that we make, instead of one cone to represent like or approximate all of the points in North America, we break it up into like 200 cones or 200 cylinders, for example. That's the way that we oftentimes would minimize that error. And also I want to point out that when I first started doing engineering design, I looked at a plan set. I expected to see like latitudes and longitudes all over it because that's what I was used to when we talked about locations on the surface of the Earth. But when we start talking about grid coordinate systems, specifically things like state plane coordinate systems, what the coordinates are going to be will be 3 distances. It'll be a northing, an easting, and an elevation. And the northing and the easting are measured from some origin point. And each state is different about this. In Oregon, for example, the origin point for our state plane coordinate systems is like out southwest of Oregon in the Pacific Ocean. The northing is simply the vertical distance, like the y coordinate relative to that origin, and the easting is the east distance from that origin, but it's measured in just feet. So you might have coordinates of, 1.5 million feet and 1.1 million feet away from some false origin. Again, that's just kind of I wouldn't call it an arbitrary convention, but just something that you might need to get used to as opposed to seeing latitudes and longitudes. So I mentioned before we have the cone type projection, we have the cylinder type projection. The transverse Mercator system is the cylinder, and the Lambert system is the cone. And this is the breakdown in terms of which states use which, and a couple states use both, which I'm not quite sure why, but they do. And Oregon is right here in the Lambert system. So we use what's called a Lambert conformal conic projection, and that looks like this. So here we have the Earth, and then we basically put a cone segment on top of it. And the critical thing here is that this cone is designed so that it coincides exactly with the surface of the Earth on these two lines right here called standard parallels. And those are critical. Those represent points where there are the length on the cone is exactly the same as the length on the Earth. And so those are points, those are lines that have zero distortion in terms of like length. So on those lines, if you measure something 1,000 feet in the real world, it would be 1,000 feet on the Lambert cone as well. However, everything not on those lines is going to have some sort of a distortion, and we kind of limit the north-south limitations of this cone in order to limit what that error would be. So there's often like a maximum error, and I don't remember off the top of my head what it is for the Lambert, but it might be 1 foot in every 10,000 feet or something like that. It can be relatively small. Also important to point out that because this is a grid system, actually I didn't draw those too great, grid system with basically X and Y coordinates, it isn't going to line up perfectly with latitudes and longitudes. There's going to be relative angles between the grid system that's set up horizontally and vertically and the meridians and the latitudes as well. And so those need to be that error, that change, that difference needs to be captured as well. And I guess I would point out that here, yes, one of the meridians is going to be non-distorted, but the rest of them, because of the convergence of the meridians as they get closer to the poles, there is going to be some inherent error. So here's a couple images of the Oregon Lambert. So in Oregon, it's split up into two different zones. We have a north zone and we have a south zone. That's because for the distortions to stay relatively low, we want to limit that height to approximately 158 miles. So we have two different zones within Oregon to limit that error as much as possible. And I also point out that these do end up, like I said, if you have a cone on top of the Earth and you cut longitudinally one side of it, you can then spread it out to a flat surface. And that's why we see, these meridians on the ends are not perfectly vertical, they're slightly turned in as a result. This is just another map showing what the relative percent error is in measurements between the Lambert projection and the geodetic representation. And I believe that the largest amount of error that we see here looks like purplish. It's about 0.1% is the maximum error in measurement that we get if we're using the Lambert projection versus the true value. Okay, so the other type of state plane coordinate system and grid system more specifically is called a transverse Mercator, which is using a cylinder, just a small portion of a cylinder, to approximate or project features from the surface of the Earth onto that, and then you can cut that cylinder on one side, spread it open, flat, and then get your grid system that way. As with the Lambert conformal conic, there are limitations about like how big this area can be and still keep a relatively small amount of distortion or error. And so here, these lines right here are where the cone intersects with the surface of the Earth, and that's where there's zero distortion. You'll notice here that this is a north-south direction as opposed to east-west for Lambert, which is totally fine. And then the limits of the projection are a little bit further. And so between the inside two lines, there's either like the actual measurement is too short or too long. It's the opposite outside of those inner two lines. But they try to balance it out so that there is some error, but it gets relatively balanced out in either direction. And this is showing you kind of like a cross-section cut of what the projection plane looks like relative to the surface of the Earth, or the surface at least of the ellipsoid, our assumed shape of the Earth. So here, if we set up the cylinder to only hit the assumed shape of the Earth at one point, we would call it a tangent projection, where there'd only be one line with a zero distortion. Most of the projections that we do in state plane coordinates, the cylinder or the cone intersects the geodetic shape in two locations. We call that a secant projection, and therefore we get kind of a balanced amount of error. And so in some places the scale is too small, and then in other places on the other side of that secant line the scale is going to be too large. So based off where you are horizontally, like your latitude and longitude, you are going to have different distortion in your projection itself. So the horizontal location is one thing that's going to affect your accuracy. Here's a much larger view of what's known as the universal transverse Mercator. So we were talking about transverse Mercators as simply a cylinder, then to approximate the grid coordinates for one location. We were talking about, the United States, but there's a universal transverse Mercator system for the entire world, where it's broken up into like almost 1,200 different projections. So 1,200 different little segments of a cylinder to approximate the curved shape of the world onto a two-dimensional surface. Now, there's not exactly 1,200. As you get closer to the poles, some of these are in red because they use quite fewer projections because there's so much less land there. But either way, quite a few different projections, and this is a pretty worldwide standard, but different than the state plane transverse Mercators, but a good like global grid system that can be used pretty much anywhere. Now, in terms of that distortion, I just want to drive home two ideas about the distortion really quick. So we just talked about one of them, is that where you are horizontally, like if you're at this location on the Earth or this location on the Earth, you will have a different distortion factor. Like if you were to measure on your map 1 mile, that might be actually longer than a mile or shorter than a mile, depending on where you are in terms of northing and easting. So your horizontal location will affect how much error or distortion you get. And I think that most people are pretty understanding of that. The trickier one is that your relative elevation to the projection plane will also affect the distortion or error. And the reason is basically like the distances as you go down to like the center of the Earth, they converge at a point. And so the higher your elevation is, you're actually like, let's say that you measure 1,000 meters on the face of the actual Earth. Well, that measurement might be represented differently on the assumed shape of the Earth, the spheroid, the geodetic surface. And that would also be different than how it's projected onto that projection plane, which might have a different elevation depending on where it's cutting through the Earth itself. And so it's not just where you are horizontally that will distort the measurements from on the projected plane versus what they are in reality. It's also the elevation that's going to affect it. So horizontal location and elevation, both of them cause distortions from the true value relative to the projected surface. So just something to keep in mind. All right, so the last thing that I want to talk about in terms of control survey, we just got done talking about the reference systems and all of that, grid coordinate systems. Your book does a little bit of discussion about project control. So if you were tasked working on a survey crew in setting up the surveying to let's say lay out staking for a project, like where grading is going to happen, set up your system so that you could measure, is this building going up perfectly vertically? maybe you even have temporary structures that you need to be able to identify what the elevations are. Um, when you're setting that up, you need to be pretty circumspect about where you're tying into. Um, for a lot of different reasons. So you're always going to have to tie into some sort of a reference system, um, but you're also oftentimes going to set up your own temporary control points to allow you to then quickly take those measurements without having to go out and move your instrument a bunch of different locations. So on the left is just an example of, let's say that we're building a building or something like that, and we're tying into some known benchmarks. I mean, it's important you need to tie into at least one elevation benchmark, and then at least two known points with the horizontal coordinates are known in order to get your survey referenced in properly. But then you can set up a bunch of different other control points, whether they're temporary or more permanent, just depends on the size and the scope of your project. And you want to think about, well, where should I put in those additional points where I could then shoot 2 points, find out exactly where I am, and then use that to measure the height of this building, or use that to measure or stake out some grading or something like that. And so some of those best practices in your book, some of them are pretty obvious, like you need to be able to see as many control points as possible. Make sure that there's going to be visibility throughout all different phases of your construction. So you've got to think and look at the plan set and say, okay, well, I'm setting up a control point right here, but in 2 months there's going to be a building in that same exact location. Or there's going to be a building between me and these control points that I need to tie into. So you've got to think about that as well. Setting temporary monuments, you don't want to put them in things that are going to move. And sometimes things seem like they shouldn't move very much, like concrete slabs, but if they're doing a bunch of work here and there and undermining the slab, you got to think about that as well. So then the other thing is you can't plan for everything perfectly. Things might change, and so having redundancies in your system is also a really good idea. And so just to think of some common sense best practices for if you were responsible for locating and measuring and laying out during different phases of a project, how would you, what strategy would you use to lay everything out? So you'd disperse it, you'd make sure you had a good line of sight, you'd put temporary monuments where they're not going to move, and you'd have redundancies. Those are kind of the big picture things that I want you to think about as you're brainstorming what you would do. We're not going to go through a whole exercise to do that. Even when we do have in-person labs, it's not something that we do, but it is something that you should be thinking about.